Good time to get started. So it's my pleasure today to welcome Dr. James Eguchi to give our colloquium. James is a really, I think, impressively interdisciplinary scholar. He's got his master's at UCLA, working with Craig Manning, where he was doing thermodynamic modeling. Maybe was involved with some experiments as well. And then he got his PhD at Rice, working with Rajdeep Gupta. And there was focused on doing experiments to understand carbon, this key element within the Earth. And then did a postdoc with Tim Lyons at UC Riverside, thinking about how Earth's interior has influenced the history of oxygen in Earth's surface environments. And now he's been here at Rutgers for just over a year now, thinking about the link between volatiles from Earth's interior and major changes in Earth's surface environments and biota, things like mass extinctions. So I think he's going to be talking about some of that work today, and we're looking forward to hearing from you, James. Thanks.
Great. Thanks for the introduction, Ben, and thank you for everyone for coming to hear about some of my research. And so as Ben mentioned, I'll be talking a lot about this role of surface-interior exchange of volatiles and how it plays a role in perhaps the sedimentary isotope records and also mass extinctions. And so, just to emphasize the importance of volatiles, I wanted to start my talk by showing this image of the terrestrial planets in our solar system. And we can see that Earth clearly stands out from the other planets due to the abundance of surface water. And the key to liquid water at Earth's surface is due to its climate that's been regulated by its atmosphere for billions of years. And the key climate regulating component is carbon dioxide. And so if we want to understand the evolution of Earth's our planet's evolution, it's important to start thinking about understanding the carbon cycle. And so in this image, I'm just showing the relative sizes of different carbon reservoirs on Earth. And we can see that the ocean atmosphere is much smaller compared to the crustal reservoir and the mantle. And so any exchange between these reservoirs could have significant effects on the ocean atmosphere system. And so now I'm just showing the subduction flux of carbon from Earth's surface to the interior. And we can see that the magnitude of this flux has the potential to subduct the entire ocean atmosphere system on the time scale of millions of years. It can also subduct the entire crustal reservoir on the time scale of about less than 2 billion years. And so the persistence of carbon in Earth's surface reservoirs likely requires efficient recycling back to Earth's surface via volcanic degassing. And it's a recent study looking at the different fluxes between Earth's surface and interior suggests that these subduction fluxes and the outgassing fluxes are essentially in balance. And it's this exchange of volatiles between Earth's surface and interior environments and the effects that this transfer has on Earth's evolution that's kind of the motivating theme behind a lot of my research. And so, as Ben mentioned, during my PhD, I was doing a lot of high pressure experiments to investigate these processes that return subductive volatiles back to the surface in processes such as melting of carbonated lithologies. And then, during the end of my PhD and during my time as a postdoc at UC Riverside, I started thinking about how this exchange of volatiles between Earth's surface and interior might be playing a role in the long-term evolution of Earth's carbon isotope records. And now, here at Rutgers, I'm trying to use fieldwork and analyses of natural samples to investigate how volatile release from large igneous provinces might be playing a role in changing Earth's climate and environment. And so this brings me to kind of the two themes that I'll be discussing during my talk today. And the first thing I want to be talking about is what role does surface interior recycling play in controlling the long-term evolution of the sedimentary carbon isotope record. And then I'll talk about how does volatile release from large igneous provinces affect the climate and environment, and I'll specifically focus on sulfur release from the Antang Java Plateau. And then I'll wrap up with some of the future directions of my work. And so in this figure, I'm showing the carbon isotope record versus time. And this record is important because it's thought to contain information about the history of life on our planet. And that's because carbon isotopes are thought to be sensitive to changes in this parameter called F-org, which is the fraction of carbon that's buried as organic carbon relative to inorganic carbonates. And so whenever this value deviates from 0 per mil in these positive carbon isotope excursions that we can kind of see during the Paleoproterozoic, and that's called the Loma-Gundi excursion, this is thought to be driven by enhanced primary productivity. And when we have negative excursions, that's thought to be driven by less primary productivity. And this connection can kind of be seen in this figure, where I'm showing the evolution of atmospheric oxygen through time. And we can see that coincident with these large positive carbon isotope excursions, we see big rises in atmospheric oxygen. And this would kind of make sense with the idea that when we have enhanced primary productivity, as suggested by the carbon isotope record, we see rises in atmospheric oxygen. And so I just want to show the simple mass balance equation that kind of shows what is actually controlling the carbon isotope record of marine carbonates. And the main parameters that controls this value is the carbon isotopic composition of carbon coming into the ocean atmosphere system, and that's dominated by volcanic degassing. Another parameter that can control this record is F-org, as I was talking about before, and also the magnitude of fractionation between that carbonate and organic carbon. And the canonical view has always been that delta C13N has been constant through time, or this would, or that the carbon isotope composition of volcanoes has remained constant through time. So the main driver of changes in this record is really this value of F-org. However, for the rest of this talk, or for this portion of the talk, I want to talk about an idea where we might, why we might think that assuming that carbon isotope, the delta 13Cn has remained constant may be a poor assumption. And so if we just look at the sedimentary isotope record, we can clearly see that it's changed through time. And we have a good idea that these sediments are being recycled and being outgassed at volcanoes. So that also gives us an idea that if these two records are tied, that the volcanic composition should also be changing through time. And so this is just a schematic to kind of show this new hypothesis on how the deep carbon cycle is actually playing a role in changing the carbon isotopes at different volcanoes. And so this canonical view probably applies to mid-ocean ridges, which are mostly sampling carbon from the depleted upper mantle. And this is always thought to be around -5 per mil. However, we also have carbon from the surface being subducted at subduction zones, both as carbonate and inorganic carbon. But as this slab is subducted and we start releasing volatiles from the slab, carbonate, inorganic or organic carbon, which metamorphoses to graphite, is actually much more refractory compared to carbonate. And so the carbon being released at arcs is likely to be preferentially derived from carbonates, which have a heavy isotopic value. And so we might expect the carbon isotope signature at arcs to be heavy compared to mid-ocean ridges. And this, after the slab has kind of passed through the subduction zone, it would have lost most of the carbonates, so it's now kind of enriched in graphitized organic carbon. And if this slab contributes to melting at intraplate volcanoes, we might expect the carbon isotopic signature at these settings to reflect more organic carbon in their source. So they might have carbon isotope values less than about -5 per mil. And so these are just some images from some of the experiments that I was doing to investigate how much that graphitized organic carbon can actually be dissolved in those silicate melts. And so this is just an image of one of the experimental capsules where we have silicate glasses in a graphite capsule, and we can measure how much of that graphite actually was transferred into the silicate melt. And relative to carbonates, the solubility of graphite is much more limited compared to the oxidized form of carbon. And this figure is just to kind of illustrate that idea as well. And so what's shown here is pressure on the y-axis and the percent of the originally subducted carbon that's going to remain in the slab as a function of that slab actually melting. And so we can see that in the black line, the amount of graphite that's retained in the slab is much higher compared to the melting out of carbonates and also these metamorphic decarbonation reactions. So this kind of would tell us that as this slab is passing through the subduction zone, that graphite is going to be retained while a lot of those carbonates are going to be released. And so if this is actually happening, then we would expect to see heavy carbon isotopes being emitted at arcs. And this is a compilation of delta 13C measurements made at arc volcanoes around the world. And we can see that a lot of these arc measurements are actually above this canonical mantle value, and that the arc average is around -3 per mil, which would be consistent with preferential sourcing of carbonates relative to organic carbon. And we would also expect to see intraplate carbon, carbon released at intraplate volcanoes to reflect this preferential enrichment of organic carbon with values of less than -5 per mil. And this is a record of of kimberlites through time, the delta C13 of kimberlites through time. And we can see that there are actually, during the Phanerozoic, values that are lighter than the canonical mantle value. And the authors suggest that this is likely due to the recycling of organic carbon after the Cambrian explosion. And so now to just kind of test this idea, we put together a simple box model. And these are just some of the major assumptions that are built into this model. So the flux of our subducted carbonate is proportional to the size of the ocean atmosphere carbon reservoir. And it's also sensitive, this value K, which is sensitive to how weatherable, or it's sensitive to weathering at Earth's surface. And we also keep the value of F org constant at 0.2 per mil. And so any of the changes in this box model are driven by changes in the the carbon isotope composition of volcanoes rather than any changes in F org. And we keep the carbon isotope composition of carbon released at mid-ocean ridges constant at around -5 per mil. And the carbon isotopes released at arcs are influenced by subducted carbonates, and the carbon isotope composition of carbon released at ocean island volcanoes is influenced by subducted organic carbon. And we're also assuming that subducted carbonates are returned to the surface on the order of tens of millions of years after initial subduction, and that the return of organic carbon is on the order of hundreds of millions of years after subduction. And so this is a result from some of those box models. And on the top, I'm showing the carbon isotope composition of different volcanic settings, with the arcs in red and the intraplate settings in black. And the, is this working? Okay. And the carbon isotope composition of marine carbonates is shown in orange. I'm also showing the carbon fluxes of the subduction zones and also different volcanic settings with arcs in red and ocean islands again in black. And this is that value of K that I was talking about, which is the strength of the weathering feedback. And it's this value that we're changing to really drive any of the perturbations in our model. And so the initial perturbation is an increase in that weathering feedback, and this causes more cations and nutrients to be delivered to the ocean, resulting in a higher subduction flux of both carbonates and organic carbon. And that's shown here in this flux here. And shortly after, that increased flux of subducted carbonates is released at arcs, which also increases the carbon isotope composition of carbon released at those arcs, which results in the initiation of a positive carbon isotope excursion in marine carbonates. And then on the order of hundreds of millions of years later, that pulse of subducted organic carbon is released at ocean islands, which decreases the carbon isotope composition of carbon being released at intraplate settings, and this ends the positive carbon isotope excursion and might even drive the negative carbon isotope excursion. Oh, sorry, I was supposed to kind of click through, but. And so as we, in order to reproduce the carbon isotope record through the Proterozoic, we just prescribed 3 increases in the weathering feedback as shown in this figure. And it becomes important to think about whether there's any reasoning behind prescribing these increased weathering fluxes at these times. And now what I'm showing on the bottom panel is the delta 18O and epsilon hafnium recorded in zircons. And this value is thought to be sensitive to how much subducted components are contributing to arc volcanism. And we can see that when we're prescribing increased weathering feedbacks in our model, we see these peaks in this zircon oxygen isotope delta 18O and epsilon hafnium record, which would be consistent with increased subducted components at this time in Earth history. And then it becomes important to kind of think about why at these times we might expect increased weathering and subduction of carbon. And what I'm showing here is the zircon count through time. And this record is thought to be sensitive to supercontinent cycles, with the peaks in this record coinciding with supercontinent assembly, and the troughs in this record coinciding with times of supercontinent breakup. And so we can see that these prescribed perturbations in our model correspond with troughs in this record, so we might assume that these times of supercontinent breakup are driving enhanced weathering and subduction of carbon, and the resulting carbon isotope excursions in the Proterozoic due to this differential recycling of carbonate and organic carbon. And this is just a schematic figure of to show why we might think that supercontinent breakup could enhance weathering and subduction of carbon. And so as continents are breaking up, it's often thought that perhaps impingement of mantle plumes leads to supercontinent breakup, and as it's breaking up, there's increased eruption of basalts along these new plate boundaries. And these new basalts are highly weatherable, so they can contribute to increased carbon burial. And also during these times, as there's some dynamic uplift from the impinging mantle plume, it could cause lowering of sea level and exposure of the continental shelves, and this could cause the carbon that's being deposited in the ocean to bypass the shelves and be easier to subduct as it bypasses the continental shelf and is deposited on the continental slopes. And so the takeaway from this portion of the talk is that the rapid release of carbonate at arcs and the delayed release of organic carbon at intraplate volcanoes might systematically change the carbon isotopes emitted at volcanoes. And when coupled with the increased subduction flux it can generate some of the large, long-lived positive carbon isotope excursions that we see in the Proterozoic. And so now I'll be moving on to this second theme of the talk, which is focused on how volatile release from large igneous provinces might affect the climate and environment, with a specific focus on the Ontong Java Plateau. And so in this figure, on the top panel, it's showing the volume of lava emitted at different lips through time. And on the bottom panel, it's showing the percentage of species that are that go extinct in some of these mass extinction events. And we can see that a lot of these mass extinction events coincide with these eruption of these lips. However, when we look at the largest lips through time, specifically the Ontong Java Plateau, we see that there's no mass extinction that coincides with this event. And so in this project, we're interested in looking at what's different about Ontong Java that could have resulted in the diminished environmental impact despite its large size relative to some of these other continental flood basalts. And so in this figure, I'm showing some of the different behaviors between carbon dioxide and sulfur release. And so in the left panel, we can see that CO2 begins to degas at tens of kilometers in the crust. So by the time this magma has traversed through tens of kilometers of the crust, it's already lost a lot of CO2. So CO2 begins to degas deep, whereas sulfur, which I'm showing on the right, this is calculated sulfur degassing from a model. And this scale is relative to the first about 5 kilometers on over here. We can see that sulfur doesn't degas until about 1.5 kilometers. So there could be this difference in degassing pressure between CO2 and sulfur, which have different effects on climate, with CO2 driving long-term warming and sulfur driving short-term cooling. And so we wanted to see whether the pressures at the seafloor could have suppressed a lot of the sulfur degassing at the Ontong Java Plateau. And so this is just the map to show where the Ontong Java Plateau is. So it's off the northeast coast of Australia, and there have been several drilling expeditions to collect samples from the Ontong Java Plateau, and these are just shown with these different points on this map. And so some of the samples that were recovered during these expeditions were pillow basalts. And so these pillow basalts, they've retained a fresh glass rim, and that's shown here. And they also have fresh olivines that contain melt inclusions. You might be able to see some of the melt inclusions in these olivine crystals, like one of these. And so for this study, we wanted to target the olivine-hosted melt inclusions, and that's because these olivines form deep in the crust, and so as they're forming, they trap this melt, and it records the conditions during entrapment. So if we want to understand what the sulfur concentrations deep in the system were, looking at olivine-hosted melt inclusions can help us do that. And so we collected different samples that had the olivine-hosted melt inclusions, and to measure their sulfur concentrations, we used the electron microprobe here at Rutgers. And these are some of the results from those measurements. And so these data points are previously measured sulfur concentrations in the pillow basalt glasses. So these sulfur concentrations record conditions during emplacement at the seafloor. And this is just to show the range of the sulfur concentrations that we measured in our melt inclusions. We haven't measured CO2 in water yet, so we can't convert it to a pressure, but we're just assuming that they're entrapped at higher pressures compared to what's erupted on the seafloor. And if we were seeing a lot of degassing of sulfur, we would expect the measurements in the melt inclusions to be higher than what's recorded in these glasses, but they show the same range, so that this is kind of telling us that we don't expect these glasses to have undergone a lot of degassing. But this model predicts that degassing commences at around 150 bars. We can kind of see that as these, in these samples that were erupted at much lower pressures, they might have lower sulfur concentrations. So these samples degass at less than 150 bars might have undergone some degassing. And so we went through and calculated the estimated sulfur degassing efficiency of all these samples from Ontong, Java, and compared it to the sulfur degassing measured in different continental flood basalts. And we can see that the degassing efficiency at Ontong, Java is much lower compared to these other continental flood basalts. And so this could be one of the reasons why Ontong, Java, the eruption of Ontong, Java had a much lower environmental impact compared to these other continental lips, perhaps because it degassed a lot less sulfur. And so the main takeaway from that portion of this talk is just that the pressures of deep submarine eruptions can suppress sulfur degassing, and that the Ontong, Java released less sulfur compared to continental lips, and this may have played a role in its muted environmental impact. And so now I just wanted to take some time to talk about some of the future work that we're planning. And so related to this Ontong, Java study, we recognize that there might be a spatio-temporal evolution in the release of gases at this setting. And this is because the early eruptions of Ontong, Java are erupting in the deep submarine setting at higher pressures. And so not much sulfur is being degassed. But as the plateau is building up and eruptions are being in place at shallower waters, you can start degassing more sulfur due to the lower pressures. And so there might be this temporal evolution of early warming followed by a transition to cooling, just as that eruption pressure at Ontong, Java decreases. And so what we're thinking about moving forward is whether this temporal evolution in the emission of gases can have any implications for continental lips. And this is because there are studies that suggest that during the eruption of continental flood basalts, there might be a period of intrusion prior to the eruption of these basalts at the surface. And so in this scenario, these intrusions could release a lot of CO2 and drive warming without releasing any sulfur. But then as this system is evolving and the flood basalts are erupting at the surface, it's at this point that you can release a lot of sulfur and drive transient cooling. And this might play a role in some of the environmental effects of continental flood basalts. So just to kind of illustrate this idea, what I'm showing here is a study looking at the evolution of euxinic conditions during the eruption of the Siberian traps. And so the color on these maps corresponds to the concentration of sulfide in these waters. And we can see that as CO2 is warming the climate, this model is really responding to enhanced microbial activity that drives euxinic waters. And so as this as the ocean is warming and we have enhanced microbial activity, this leads to higher respiration, and this could develop anoxic and euxinic waters. And so in this scenario, they can see that as they warm the climate by adding CO2 into the system, they start developing euxinic shallow waters. And these dots, the circles on this figure, correspond to proxies of proxy records of euxinic conditions at these locations. So they are able to reproduce euxinia at some locations, but not at others. And so this is a work from one of Ben's papers, and it shows the competing effects of warming driven by CO2 and cooling driven by the release of sulfur on the strength of overturning in the ocean. And we can see that in this blue record, which only includes warming from CO2, that there's reduced overturning in the oceans. But when we have these pulses of sulfur release, that drives enhanced overturning in the ocean. And so what we want to explore is whether initial periods of warming driven by CO2 release could build up euxinic and anoxic deep waters. And then once you move into this eruptive phase of flood basalts and drive some cooling by the release of sulfur, this could enhance the ocean overturning and perhaps cause shoaling of euxinic waters that could contribute to some of this mass extinction events. And this is a record to kind of show that perhaps we might be seeing this clues of this, we might be seeing hints of this kind of temporal evolution from CO2 release to sulfur release. And so on the left panel, it's showing the carbon isotope compositions through the end Permian mass extinction. And this blue region is showing the extinction event itself. And so we can see that the carbon isotope excursion actually begins before any of the mass extinction, before the initiation of the mass extinction. And we also can see from oxygen isotopes that there may have been warming prior to the extinction. However, when we look at the sulfur isotope record, you might be able to argue that it remains flat prior to the mass extinction event, and we don't get that sulfur isotope excursion until we actually have the initiation of the mass extinction. And so this could be telling us that there could be a period of warming prior to the extinction, and then the eruption of sulfur could be an important part of driving this mass extinction. And this could be due to buildup of anoxic and euxinic deep waters, and then this could be enhanced. This extinction could be enhanced by the strengthened overturn of the ocean, bringing some of those toxic waters closer to the surface. And so this is another project that we're thinking about to kind of test that this idea that differential mantle recycling of carbon could be driving a lot of the secular evolution in the carbon isotope records. And so to test this model, one thing that we can look at is this model makes predictions on what the carbon isotope composition evolution should be at different volcanic settings. So as we look at this arc value, which is shown in green, we might expect arcs to become heavier at these times. And if we look at the ocean island, the intraplate settings, we can see that there are specific times in Earth history where the model is predicting that values decrease. And so this is just an overlay. I've overlaid that kimberlite data from an earlier slide onto the predicted carbon isotope values at intraplate settings through time. And you might be able to see that here in the Ediacaran, when the model is predicting a sharp decrease in the carbon isotope values of intraplate settings, this is when the record actually shows the most negative values in the kimberlites. And also when, and then as this model is predicting recovery into more normal mantle values, we do see that in this record of values around minus per mil. And then as we proceed into the Phanerozoic, the model is still predicting somewhat lower values, and this could be consistent with this record. However, there's a lot of gaps in this record, and one way we're thinking about looking to fill in this gap is that there's a lot of carbon isotope measurements in carbonatites. And so these carbonatites could be tapping some of this, these deeply recycled volatiles and at intraplate settings. So we want to go through this record and fill in this gap to see if we can, if there's any agreement between what the model's predicting and what's actually being recorded in the geologic record. And so just to finish up, I think I wanted to end by just putting back some of the takeaways from these two different portions of the talk. And the first would be the rapid release of carbonated arcs and the delayed release of organic carbon at intraplate volcanoes can systematically change carbon isotopes through time. And when coupled with increased carbon subduction, it can generate some of the large, long-lived carbon isotope excursions that we saw in the Proterozoic. And also, the pressures of deep submarine lips can suppress sulfur degassing, and this suppression of sulfur at Ontong Java may have played a role in its muted environmental impact. And I think I'll finish there and take any questions.
Questions for James? Maybe start with the student. Claude has a question.
Yeah. Oh. So you showed the Ontong Java Plateau, and you showed there was no, because it's deep sea, large igneous province. You showed there was no extinction. But then you showed the Kerguelen Plateau, which is also a deep sea, large igneous province, and there was a mass extinction after that.
Let's see.
Well, not mass, but an extinction.
Yeah, so I guess it doesn't completely line up with the Kerguelen. It's somewhat prior, but yeah, that's something that I should look into the coincidence of Kerguelen with some extinction events as well.
Very early on, you proposed there was a correlation between supercontinent breakup and your carbon isotope excursions.
Yeah.
So one of the big supercontinents was Nuna or Columbia. And
Nuna.
that broke up and led to the assembly of Vodenia sometime afterwards. And I didn't see anywhere where the breakup of Nuna was correlated with any carbon isotopic excursion.
So I think
Am I wrong?
the breakup of Nuna was at around 1.4 billion years, I think.
Yeah, but it was protracted, about 1.4.
Yeah, so I think we do impose some perturbation at that time, but it's much smaller compared to what's at the Paleoproterozoic and Neoproterozoic. And I think also there's, oh yeah, the carbon isotope excursion is not there. And I think there's been arguments that the breakup of Nuna was not as intense as the breakup of some of these other supercontinents. And also, I think it might make sense because during these other times in Earth history, during the Paleoproterozoic and Neoproterozoic, we also see evidence for snowball Earths. And so I think that this is a sign that carbon drawdown is especially intense at this time. But we don't see evidence for this during the breakup of Nuna around 1.4. So even though there was possibly some breakup, it might not have been as intense as some of these other times in Earth history.
That was an interesting talk, so thank you. And I was wondering if you go to your box model.
Oh.
Is there a reason why you went with a box model as opposed to looking at, say, a geodynamic model that has a little bit more complexity to the feedbacks that you are laying out here?
Well, I think this was just kind of, at this point, kind of a proof of concept. So we just went with something that was simple. But no, I agree that adding in something like a geodynamics to actually see the timescales of recycling, I think that would be something that would be important and could really strengthen this argument. So,
just a quick follow-up: do you expect to see differences in the outcomes if you had a geodynamic model compared to the static box model?
Well, I would predict probably not. I think because I think there are reasons to expect that, and there have been studies that are looking at the time scale of recycling from subduction to arcs, and that is really, I think that's what would change the most from a geodynamic model, just this time scale of recycling. And if it agrees that recycling at arcs is on the order of tens of millions of years, and that the return to intraplate settings is on the order of 100 million years, then I don't think we would see a big difference. But I guess it's important to kind of confirm that. But, and I think there's reason to expect that maybe that if we just assume that as we subduct down to the core mantle boundary, across and back up in kind of a symmetrical convective cell, we're traveling on the order of 10,000 kilometers, and if the plates are moving on the order of 1 to 10 centimeters per year, that comes out to 100 million to a billion year time scale. So I think that this time scale is within that what might be shown in some of these more dynamic models.
I was wondering about your sulfur degassing model. So the lithostatic stress imparted by just like the weight of the rock would always be a factor of 3 higher than water because of density, right? So, so in that case, why is it that volcanoes, what is something so special about LIPs that a tiny bit of pressure, like underwater, suppresses sulfur degassing, but over land, for example, from places like St. Helens, we see substantial amount of sulfur coming out, even though you have massive kilometers of rock putting in pressure.
So I think in this, there are ideas that you can have these volcanic conduits, and there's actually convection of the magma moves closer to the surface and comes down. So perhaps just as it's nearing the surface, you could have some degassing. And maybe not the entire degassing driven by, not all of that sulfur is being released from the deepest portion of the magma chamber.
But you're saying the lack of degassing or the lower degassing efficiency is because these LIPs are deep underwater, right?
Yes, I think.
Yeah, so I guess then, why is that the case? But then you can have 5 kilometer tall volcano on top of the land. Isn't there more pressure from the volcano itself than 5 kilometer worth of water?
So I guess what I was getting at, there could be some migration of magma closer to the surface, away from 5 kilometers deep beneath the volcano, closer to the surface, and there could be some degassing as this magma is migrating closer to the surface, but okay.
Just following up with this point, actually, it's actually an interesting thing to explore. Because I feel like it's the effectiveness of the conduit to actually release the gas is it's more important, because I feel like because if you think about the mobility of these two phases of materials, we have gases and water. Gases are much more mobile than water. It should be, whenever it has reached the conduit, something that can release these gases. It will just release. It will just release, right? So.
Sorry, could you repeat that? Or.
So I'm thinking about the mobility. So mobility of these gases versus water, because I think the second takeaway that you said it's because of the depth of the water. Right, because it's on the seafloor and we have water column right above it. I feel like if there are gases there in the magma, and then if it comes in contact with water, it'll be released easily because it's much more mobile than liquid.
Okay, and then.
Right?
Yeah, so I think as, I think gas release at the seafloor is going to interact with the water. It could be dissolved in the water and change ocean chemistry, or it could be, I'm not sure that it's going to be, I guess I'm a little unsure of what your question was. Sorry.
Okay, then just a follow-up question.
Okay.
So if we see the suppression on sulfur, when we see it, do we see the suppression on other, or other types of gas?
Oh, so I think the thing about sulfur compared to perhaps CO2 is that CO2 can start degassing much deeper within the crust, up to tens of kilometers, compared to sulfur, which we're arguing might not be released until much shallower. So I think that CO2, once it degasses, can travel through the crust and make its way to the ocean, and then it could be released to the atmosphere on timescales of ocean circulation, I think, as that deep water interacts with the surface. Is that, sorry, okay.
Maybe one more question. Looks like Mark has a question.
So good talk. You mentioned that, I think you said increased overturning circulation will make the euthentic waters at the bottom even bring them up to the top and make it what cause mass extinctions. Can you talk about the mechanism where increasing the overturning circulation will cause mass extinctions?
So I think that the concentration, like this euxinic waters, high levels of H2S is toxic to a lot of different organisms. So if you enhance overturning of these deep euxinic waters and shoal some of those high sulfidic concentrations, that could make the environments for some of these shallower water organisms now more toxic due to the higher concentrations of sulfides.
All right, let's thank James again.